Hey folks, thanks for tuning in. We're talking today about Taylor series. We began the other day by introducing the idea, and you can see the definition of the Taylor series here. If it's centered at 0, we call it a Maclaurin series, but otherwise we have a Taylor series centered at C, and we have this nice formula. And what it relies on is the function being infinitely differentiable. In other words, we can just keep differentiating again and again and again, and so calculate these higher and higher derivatives, because that's what we need to write out the series. And we found two important Maclaurin series in particular, e to the x and the cosine of x. And there's connections between these. You can see they look very similar. The cosine involves the odd terms in here, but is alternating. I wrote down the series for sine last time. We could actually see the series for sine pretty easily, because imagine I differentiate that series. Imagine I differentiate cosine. Well, the derivative of cosine, you know, is negative sine. Apparently I don't know. It's negative sine of x. And that's going to be, while writing out, I can just do it from the general form, taking the derivative term-wise. The derivative of the first one is 0. The next one's going to bring a 2 down. We get this term, right? The 2n comes down. We reduce the power by 1. I still am in principle going from 0 to infinity. And notice here that when n is equal to 0, that's our starting point when we start writing this series out. When n is equal to 0, 2n is equal to 0. 2n factorial is 1, but 2n is equal to 0. And so that's going to make the first term disappear. There's really no first term in this series when n equals 0, because it's just producing 0. And the reason for that is because when we take the cosine term and we differentiate it, we're differentiating 1. The derivative of 1 is 0. So that's what this is reflecting. So we can rewrite this so the summation starts here at 1 instead of at 0, because we don't lose anything, right? When we started at 0, it was already 0. Now there's a 2n and a 2n factorial here. Just remembering what 2n factorial is, it's going to be literally the product of the first 2n positive integers multiplied together. So if I were to cancel out the 2n, this is all in our denominator, remember, and I'm going to cancel the 2n with something in the numerator, so that goes away. What we'll be left with here is the product of the first 2n minus 1 integers. So we've got one integer left. So this is going to cancel with the factorial in the denominator to create 2n minus 1 factorial. So let's put that together. What we have here is the expression from the previous page, and then simplified with that piece of algebra I was just talking about. It's going to cancel one of the 2n there, and it's going to leave everything but that last term. And so this is the series for the negative sine of x. So I can cancel the negative from both sides and end up with one less power here. And here is our Maclaurin series for the sine of x. We can write this out, right? When n is equal to 1, this is going to be minus 1 to the 0. But if n is 1, this power here will be 1. So our first term is going to be just x to the 1 divided by 1 factorial, which is 1. And then the next term, when x is 2, it's going to be a negative, because this is minus 1 to the power of 1. But if n is 2, then this is x cubed. So we'll get x cubed, the next odd number, in other words, over 3 factorial. The next one's going to be the next odd number is x to the 5, because this is producing odds, right? 2n minus 1 produces odd numbers. And so this is 3 factorial, x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. The next term's going to be positive x to the 9 over 9 factorial. And we're just going to pick up all of the odd powers in an alternating series like this. And we've seen this before. I didn't derive it last time, but I presented it. And so when we compare it with the series that we saw before, these are the same, right? This is the series in the book. Now, it's written a little differently because they use the term 2n plus 1 as the power and as the numerator. We're using 2n minus 1, but we're also starting with n equals 1, and they're starting with n equals 0. So these are producing the same series, but they're producing their odd numbers with the formula 2n plus 1, which means you have to start at 0 if you want the first power to be 1. Whereas we're using the formula 2n minus 1, which means we need to start with 1 if we want the first power to be 1. So these are exactly the same series, even though they might look a little different. Concentrate on the fact that this is x to the odd power divided by odd factorial, and then the minus 1 to a power is chosen so that the first term has a positive in front of it. Right? There's a positive there. And that's what this is producing because n equals 0 to begin with. That's what this is producing because n equals 1 to begin with. All right, so there are other connections between sine and cosine and exponential when we have their Maclaurin series that we can see, so let's have a look at those. So you see here the Maclaurin series for cosine, the Maclaurin series for sine. Again, I've commented before, these are all the odd even powers, these are all the odd powers, all divided by factorials. Whereas the exponential contains all of the powers divided by the corresponding factorials. So apart from this not being an alternating series, it's almost like these have some sort of connection. And that connection involves complex numbers. Now hopefully you've encountered these before. Complex numbers are numbers that can be written as a plus bi, where a and b are some real numbers, and I squared is negative 1. So for example, a complex number looks like 3 minus 2i. Or another complex number might be, 5 plus pi I. So that, and the order is not important here, 5i plus 5 is the same thing. So one of them is the imaginary piece, and one of them's the real piece. The imaginary piece is the piece that has the I multiplying it. So we would say pi is the imaginary piece, and 5 is the real piece here. And the key is coming from this idea that I squared equals minus 1. Now, no real number when you square it is negative. And so we've invented this. This is called the imaginary number I. And it's not a real number. This is what creates this field of complex numbers, because we're inventing a number that's not real. You can't find this number on the number line. The whole point of the real numbers is if I draw the x-axis, every real number lives on here somewhere, right? Not to scale. But every real number is on here somewhere. Negative square root of 2 is on there, 3 is on there, pi is on there, any real number you care to name is on there. That's why infinity is not a real number, because I can't draw infinity on this axis. Infinity is just the concept of getting bigger and bigger and bigger off to the right. And so infinity is not a real number. In the same sense, this I is not a real number. But it has these nice properties, and the most important one, the defining one, is that I squared is equal to 1. So let's look at this exponential a bit more closely. We're going to use the series to calculate e to the ix, where I is this imaginary number. So I squared, we know, is 1. So I squared, we know, is minus 1. And I, well, that's just I, right? So I'm going to start writing this thing out. So using this expression for the exponentials Maclaurin series, everywhere I had an x, I'm going to replace it with an ix, because that's all I've done here, right? I've got an ix in the denominator, in the numerator there. So everywhere I had an x, I'm going to replace it with ix. So this is ix, and this is ix. But now that's squared, divided by 2 factorial, and the next one's going to be ix, but now it's cubed, divided by 3 factorial. Aren't complex numbers fun? All I'm doing is substituting here and writing them out, and I can write out as many terms as I like, and I like writing out terms, so I'm just going to keep going, right, over 5 factorial, ix to the power of 6 over 6 factorial. This goes on forever because it's an infinite series. So I can simplify this, because in each case we're just squaring and then cubing and then adding, raising to the 4th power, these I things. But I can calculate powers of I. I know I squared is negative 1, for example. What's I cubed? Well, I cubed, one way to think about it is it's I times I squared. Well, I squared is negative 1. So this has to be negative I. What's I to the power of 4? Well, one way of thinking about it is that's I squared squared. So that's minus 1. I squared is negative 1. So that's minus 1 squared. And that's 1. I to the 5. Every term is just the previous one multiplied by I, right? What do I do to move from a 4th power to a 5th power? I multiply by I. So I've got a 1 here. When I multiply by I get I. Now I've got an I here. When I multiply by I get I squared, and that's going to be negative 1. And then I to the 7, that's going to be this multiplied by I, which is minus I. I to the 8 is that multiplied by I, so it's negative I squared, which is now negative negative 1, which is positive 1. And so hopefully you can see a pattern's emerging. We've got I minus 1 minus I 1. And then it restarts. I minus 1 minus I 1. And then it continues repeating like that. So I can write this whole expression down by simplifying. Everything that's an I, in fact everything that's an odd power of I, notice everything that's an odd power of I, there's 1, there's 1, there's 1. All it does is alternate between I and minus I. So the odd powers are going to be I minus I minus I. So I've got an ix, and then The even powers just alternate between positive and negative 1. This one is going to be, negative I cubed is negative I. So this is I x cubed over 3 factorial. And the next one is, well, it's going to be I to the 4 is positive. That was right. So it's positive x to the 4 over 4 factorial. The next one is maybe negative I to the 5. Nope, that's positive I x to the 5 over 5 factorial. The next one's x to the 6, that's negative 1. So this is x to the 6 over 6 factorial. The next one's going to be x to the 7, which is minus I x to the 7 over 7 factorial plus, that keeps going. So notice half the terms end up with i's in them and half of them don't. So I'm going to have this, a bunch of terms with i's in them and a bunch of terms that don't. So the ones that don't have an I in them, notice, are all of the even powers. So I'm going to write them in this bracket. I've got a 1, and then I've got an x squared over 2 factorial, and then I've got an x to the 4 over 4 factorial, and then I've got a negative x to the 6 over 6 factorial, and then I've got plus dot dot dot. But all the ones that still have i's in them, they're all the odd terms. I'm going to write them in this bracket. There's I times x. I'm just factoring the I out. I times x. And then there's minus I times x cubed over 3 factorial. Took the negative out. And the next one's plus x to the 5. I ran out of room in the previous page, so let's just rewrite it here. This is x to the 5 over 5 factorial. As I'm gathering those terms, we're picking up, as I said, all of the odd ones. And then that continues. They're both alternating. This is an alternating series with all the positive powers of x. This is an alternating series with all the negative powers of x. There's an imaginary number out there. And these things certainly should look familiar because we've seen them before. This is just the cosine of x. This is the cosine of x. And this second one is the sine. In other words, the first bracket contains the Maclaurin series for the cosine of x. The second contains the Maclaurin series for the sine of x. And so quite surprisingly, what we've shown is that e to the ix is equal to the cosine of x. So we take an exponential with an imaginary number up there, and what we end up with is a complex number, cosine x, that's real, plus I times the sine of x. So this is an imaginary number because sine of x and cosine of x are real numbers. They're just our usual functions, but then we've got I multiplied there. So this is known as Euler's formula and gives us a powerful connection between the exponential of a complex number and the cosines and sines of the real part of the x, and then that I appearing. So as an example, we could plug in, let's say pi. Let's make x equals pi here, because then we get e to the I pi is equal to the cosine of pi plus I times the sine of pi. Well, the sine of pi is 0, so this term is 0, and the cosine of pi is negative 1. So this is I to the I pi equals negative 1. Or another way you might have seen it is this formula that connects all of the kind of fundamental basic constants of mathematics in one formula. E to the I pi plus 1 is equal to 0. So we've got the 1 in there and the pi and the exponential. And it's quite surprising that this connection exists. And it's a cute mathematical thing, but you'll also find as you go on and take classes, if you're an engineer or a physics major, that this formula underlies our understanding of anything that involves mechanical, wave motion. So waves in the ocean, obviously, but anything that oscillates, including electrical systems, right? Alternating power systems, fluid flow in channels and in the ocean, and fluid flow in the air, because the air is a fluid. So meteorology, our understanding of and the existence of meteorological models that run on supercomputers to tell us what the weather is going to be like, they rely on this identification. It's the mathematical basis for so much of what we do. So it seems like a cute observation based on these Maclaurin series, but it's actually a really fundamental mathematical result. So isn't it cool? We could do that in this class. So we've seen this fun fact. You can take them to trivia parties and stuff. Let's do another application of these Taylor series where we see why they can be really useful. So we're asked here to find the definite integral of this exponential, and this is not an integral we can calculate. We can't do that explicitly. by which I mean there's no closed form formula for the integral of e to the minus x squared. We can integrate e to the x, we can integrate lots of things. We could integrate x e to the minus x squared because that's a Calc 1 kind of substitution. But there's no closed form formula that will tell us what that integral is going to give us. And yet if you draw the graph of this thing, this is just a bell curve, this is a Gaussian, this is a well-defined area, it's not even an improper integral. It's really easy to see that that integral must have a value, right? Because that value is just the area under the curve between 0 and 1. And the curve is a really nice simple shape. It's a normal distribution. So we need to be able to integrate this. And our approach is to use a power series, because we can find a power series for the exponential, because we have this formula for e to the x. And so we can use that to build a Taylor series for e to the x squared. Now, I could take e to the minus x squared. I could take e to the minus x squared and I could start differentiating it and doing all of those things to find the Maclaurin series. But why would I bother when I've got this formula and I can just plug in? So this is minus x squared, and then the next term is minus x squared. Everywhere I see an x, I'm plugging in negative x squared, right? Because what I had here is being replaced with negative x squared. And so I'm just going through in this power series and replacing every occurrence with negative x squared. And that's going to go on forever. And in fact, I could do that in the general formula. So this is going to be the sum from 0 to infinity. This isn't alternating. It's just going to be x to the power of n divided by n factorial. Right? 1 over 1 factorial x squared over 2 factorial x cubed over 3 factorial. But I'm plugging x squared in where I had x. So here's our power series for e to the minus x squared. And that I can integrate and evaluate between 0 and 1. Just simplifying it a little bit, maybe it will look simpler or look nicer, we're going to end up with something like this, right? X to the 6. We're only going to have even terms. So this is x to the 8 over 4 factorial and so on. It's an alternating series, and that can obviously be simplified as well. Just rearranging these terms, I've got minus 1 to the n, x to the 2n over n factorial. And you might say, hang on, that looks like cosine. Well, it would be cosine if this was a 4 factorial and this was a 6 factorial and that was an 8 factorial. So it's close, but it isn't cosine. And you can kind of tell the shape of cosine is similar to this, but obviously not the same. So we've got this power series, and we can use the result that we're allowed to integrate power series to find this integral. So here's the series and the integral we want to find, and we can do it term by term. Right? What we can do is just literally write down that series inside the integral and then start integrating it. We're going to end up with a bunch of terms, and then we can extract from that the general form, or we could integrate this general expression. So let's just do the series term by term. Integrating each of these is fairly straightforward, right? We're not changing the factorial in the bottom. What we are changing is the power and dividing by that power. So the next one's going to be x to the 7 over 7 times 3 factorial, and then the next one's going to be, well, it would have been x to the 9 over 9 times 4 factorial minus ... Plus there's going to be a constant, and I'm going to write that constant at the front because otherwise it gets confusing to have it written at the back, because when I do an integral there has to be a constant. So this is the most general antiderivative. We could do it as well using the general formula. Right? Whichever of these you're most comfortable with, go ahead and do it, because what I'm going to get, the whole idea of my series, and we had a theorem way back when, the whole idea of the theorem was that we can integrate term by term, and one way to think about that is I'm going to integrate each of these pieces, each of the terms, and then I'm going to add them up. So when I integrate each of these, the minus 1's a constant, the n factorial is a constant, so the integral is going to come out to be, we're going to increase the power by 1, so the minus 1's not changing. We're going to increase the power by 1, so we're going to get x to the power of 2n plus 1, and then we're going to divide by that number. So 2n plus 1 appears down the bottom, times the n factorial, which was already there, and we need to add a constant. And if you compare these two, they're the same. Right? The first term is going to be x to the 1 over 1 times n factorial, which is just 1 factorial. The next one's more interesting. When n is 1, you've got a negative sign. It's going to be x cubed over 3 times 1 factorial, which is what we have there. And then so on. You can see the n plus 1 is appearing here. It matches the power up the top. these are equivalent. Now, what I need to do is evaluate this at endpoints. We can use any antiderivative when we want to find the definite integral. So if we can use any antiderivative, we can just take that constant to be 0, right? Because we're going to find an antiderivative. This is, if you like, the general antiderivative. But I really only want this to be able to find the antiderivative between 0 and 1, that definite integral. And so I can drop the constant. It'll cancel anyway. So let's do the integral. So we want to find this antiderivative, the general antiderivative. Sorry, we want to find the definite integral. We've got an antiderivative. It's just this expression. I put the constant equal to 0. So all I really do is evaluate it between 0 and 1. This is the antiderivative. Evaluate between 0 and 1. And that gives us just a series we can write down. Right? And it's even easier if I've done it using the general formula, because you can see all the x's are just, I'm literally plugging in 1 here. 3 factorial plus 1 to the 9 over 9 times 4 factorial plus, well, that'd be a negative actually, dot, dot, dot. You know, if you like, this is 1 cubed, this is 1 to the 5, and this is 1 to the 7, and this is 1 to the 9. And then I'm going to plug in 0. What happens when I plug in 0? Well, you get 0 minus 1/3, 0 cubed plus 0 to the 5 over, what is it, 5 times 2 factorial minus dot, dot, dot. These are all 0. Right? The value of the function is 0 there. And so we have our final result. This is just 1 minus 1/3 plus 1 over 5 times 2 factorial. So we might not be able to do this integral formally in the sense that I can write down a value for it, but I can use the partial sums here to approximate the value. Or I could write this final thing in terms of the general form, and you can see this is just going to be 1 to the n. So this is going to be an alternating series, minus 1 to the n, over, well, there's going to be a 2n plus 1 and an n factorial. And n goes from 0 to infinity, the way we've got it set up. That's another way of writing this term. And you can just literally plug x equals 1 and x equals 0 in here to evaluate this thing, because that's all I did. So we could sum this up and use it to estimate the value. So estimating this, we can do it using partial sums. Remember how we defined the idea of convergence from a series to be the requirement that the partial sums converge. So we can just start building partial sums here, right? The first partial sum is just the sum of the first one term, and that's obviously 1. The second partial sum is the sum of the first 2 terms in the series, and that's obviously 1 minus 1/3. So that's 2/3, or about 0.667 something recurring. Not 7 recurring, but 6 recurring, right? 6 recurring. The third partial sum is going to be the 1 minus 1/3 plus 1/10, because 2 factorial is 2, so we end up with a 10th there, and that one literally just adds a 10th to the number we had before, so 0.7666 recurring, right? And then the fourth partial sum is just going to subtract a 49th, because it's 3 factorial is 6 times 7, and that's going to give us, well, and look what's happening with these. This is an alternating series, so we start with 1 and then we subtract something. We subtract a third, but then we add on a 10th. So each time we subtract, we make it smaller. Each time we add, we make it bigger, obviously, but each event is a smaller change, right? Because if this alternating series converges, we know that the b sub n is a decreasing series. So the thing we're adding or subtracting is getting smaller as we go along. And it has to converge to 0. That's the requirement of the alternating series test. So then this is 0.766, but then we're going to subtract something. So it's down to 7.4 to something. If we look at the fifth term, we're going to add, or the fifth partial sum, we're going to add the next term on, and it's going to jump back up to 0.747, and so on. And as you build this series, we find that Sn, the nth partial sum, at least to 6 decimal places, stops changing. It starts getting closer to 0.746824. It's changing in the decimal places as n gets larger. It keeps changing in these decimal places. Obviously, it will never converge to a fixed number until we've got an infinite number of terms added on. But in terms of a limited approximation, 0.746 is pretty good, and you can see we're almost there at this point. And what that means is that the integral between 0 and 1 of this exponential, e to the minus x squared, that is about 0.746824 at least to 6 decimal places. So we can use these power series to perform an integral that we can't do with any other Calc 1 or Calc 2 knowledge because we don't have a general antiderivative for that function. Remember the idea, this is a continuous function, the definite integral exists, we just don't know how to find it. What we can do with Taylor series is use them to build a power series approximation or a series approximation to the value, and then we can make this value as accurate as we like, and that's the key idea. Where's this useful? Well, these are the values that are used in statistics because this is the normal distribution, and so these are what's used for probability estimates when you're looking at those when you're looking at areas under that curve. If you've taken a prob class, you've seen something like that. So this is a really powerful idea that Taylor series gives us a way to answer questions that we couldn't otherwise approach. And look, this final discussion has brought back in the ideas of power series and partial sums and all of the things that we talked about as we built this stuff up. So I hope that was fun. That's the last material that we're going to talk about this semester. So it's time for a cheer. Thanks for tuning in. Have a great day.